Hey, boys and girls. What up? So, oh God, showtime? Got something stuck in my throat. I think it's a cat hair. Hold on.
When you're a cat owner, you kind of just get acclimated to the fact that your cat's hair is going to get on everything you own and everything you eat and drink, and it just kind of applies itself to everything in your life. So you just
except for when you get one inside your lung. That's a little too far. It's like
the worst is when I'm petting my cat and then I got like an itch on my face, so I scratch my face and now I've got a cat hair on my face.
Oh yeah, and you can't get rid of it.
Yeah, and it keeps creeping closer to my eye as I'm trying to get rid of it. Like it does. Yeah.
Yeah, impossible to get rid of. Amazing. And then when I vacuum, I fill up my entire vacuum with like they should be bald for all the fucking hair they lose. Jesus Christ.
You can come up with all kinds of creative uses for their hair. You can make a sweater out of it, a nifty little sweater, or you could use it to make a new cat. Yeah.
Yeah. So what the hell is wrong with that? Why doesn't that work anymore? Okay, well, maybe this one. Oh, that doesn't work either. Nothing works. Cinema layout. I don't know what the fuck is going on here.
So the subject today is carbon chemistry, right?
Carbon chemistry, yeah. And the okay, where we're headed is here. Basically, this is a protein, and why proteins are drawn that way and why they fold. Now, this is ferritin. These things get together and they form these huge clusters that basically hang on to iron in your body. Mm-hmm. You can see that. It's kind of cool. You can look down the coils. You can kind of see down the coils. And this is the alpha fold stuff. And these all get together.
This is the stuff that took what T was doing, T and his team, and it just blew it out of the water. It made it look, obsolete, even though what they were doing was just a few short years ago.
Yep. And this is a little drawing of, it was what I asked ChatGPT to give me a drawing of 18 red marbles and 20 blue ones. So one of the things that the overall direction that I'm heading, and I'm not going to do it all today. It's not all going to happen today. But now, when you imagine a protein space if you have 100 amino acids, there's 20 ways for the first one, 20 possibilities for the first one, times 20 for the second, times 20 times 20. So you have 20 to the 100th power, basically, which is 10 to the 130th power.
Yeah.
So you have 10 to the 130th.
It's a very, very high number. Right. Like I think it's approaching a number that's so large that it's like bigger than the number of total atoms in the universe or some crap like that.
Right. And so the creationists they'll cite Douglas Axe's dumb article where he says that basically there's only one in 10 to the 77th power that's functional, basically. Okay, or 1 to the 70th is something they'll say. So 1 over 10 to the 70th proteins that's functional. So that means, oh my God, 10 to the 70th are not functional. Well, that also means that 10 to the 60th are functional because we have 10 to the 130 altogether. So here's how many functional proteins you would have by that logic, right? You follow that?
Yeah. It's
So,
a simple
this adds up to
simple
yeah.
subtraction there, right? We're taking
Yeah.
130
Yeah.
and subtracting 70 from it, and we're ending up with
Correct.
60.
Right. And that's a lot. I mean, so, you know, they never talk about that part, right? So basically, and the other thing is what I tried to show with this little illustration here is that if you look at the protein space, right, and you say all the red ones are functional and all the blue ones are kind of neutral and floating around and they fold and they do something, but they're not really functional, particularly, and the blue ones are non-functional, right? You can see that in a real simple ass space like this, which isn't really what the protein space looks like. You can't imagine what the protein space looks like because it's 20 dimensions and it's or worse. Anyway, so you can see that, you know, there's a possibility of hitting functional combinations with not so many mutations, and anyway, but it's all about how proteins fold, and it's about figuring out, you know, what the hell this is. And
that is a big part of why the answer is in biochemistry, right? Is because
right. Yep.
part of why proteins fold the way they do is just the properties of matter. Like anything else, living things are made of matter, which is stuff that has mass and occupies space, and stuff that has mass and occupies space has properties. And some of the properties this particular chemical compound has, some of the side chains are hydrophobic, some of them are hydrophilic. That means they either repel from water or they attract to water. That is one thing that I've read about. There's a lot when it goes to protein synthesis that is still way over my head. I'm trying to learn the subject, but there's a lot to it. But that's one of the things that we figured out as we were kind of unlocking more and more how proteins fold, is that ionic forces, property of the chemicals that make the protein itself, are a big part of how they fold the way they do.
Yeah, and all that science started in the 60s and the 50s and the 60s. And by the time 2000 rolled around, we're ready for the next steps, you know, which were, and now that the 2020s have rolled around, we're ready for AI. But each of these things is an amino acid. You can see how that little square lights up in red when I move my cursor over it. Okay, this one is
that's
leucine.
really cool. They have the whole strand broken down into amino acids. And what are we looking at right now? Would this be
this
is
ferritin.
The tertiary structure? Is this the quaternary structure? We're looking at the primary structure here, aren't we?
Okay, no, tertiary. Primary structure would be right here. Let's see if I can. Why I can't.
So for anyone in the audience who's watching that doesn't understand, what I'm asking Mike is, when we look at proteins and DNA and a couple of biomolecules that are really complex, is that they have layers of structure. They have a primary structure, a secondary structure, a tertiary structure, and a quaternary structure. And I'm forgetting right now precisely what each one is. I'm really out of it today, but maybe Mike remembers what the meanings of the different levels of structure are, and he can tell us.
So this is the primary structure, which would be the amino acid sequence, right?
Right. Yeah.
So this shows 100, I think it's 182 amino acids. It starts out with methionine, which is that ATG start codon. So proteins typically start out with an M. And you go down here and you look at, let's see, Y. Now I screwed everything up there. Let's see, I gotta make them big again. Because I kind of, oh, there we go. Okay, now he's big again. Now this would be the secondary structure would be the coils, like coils, and we have down here, I think we have a beta sheet, which we're not ready to explain yet. But these are basically alpha helices, which are ubiquitous in protein folding. It's very easy for that to happen. We have 4 alpha helices right here, and they're lined up in like a column. I think this one is called anti-parallel, meaning they point in different directions, if you see it. But anyway, each of these things, if I can get both on the screen at the same time, let's go up here. Now, if I
asked an AI real quick, Mike, to help explain it, to make it more accurate and easier for us. So the primary structure, first degree, is the linear sequence of amino acids in the polypeptide chain, just like you said, Mike. The secondary structure refers to the local folding or coiling of the polypeptide backbone into regular repeating arrangements, just like you said, Mike. The tertiary structure is the overall 3-dimensional shape of a single complete polypeptide chain. Is that what we're looking at here?
Yeah. This is one.
So we're looking at the tertiary structure. And then the quaternary structure refers to the arrangement and interaction of multiple polypeptide chains to form a single functional protein complex. So big layers of structure. The first layer just looks like, if you could represent it as like dots connected by lines, and those are an amino acid. Then the secondary structure is kind of a helix, where it is several of those dots connected by lines in a helical shape. And then the tertiary structure is several helical shapes folded into a big and then the quaternary structure, it's almost like different dimensions, like you said, like going from 1-dimensional to 2-dimensional to 3 to 4. Yeah, it's real fascinating. I'm just starting to learn about this stuff in college, and I don't understand it as well as I would like. So, but yes, it is super cool.
Yep. This is the quaternary structure. This is ferritin,
right,
and a whole bunch of those. So this one right here is one protein, and a whole bunch of, I think, 24 proteins get together, and smack in the middle of that, they grab a little iron atom and they keep it safe, basically. So right in this little pocket here, they'll grab an iron ion, basically. Yeah. We got a question, Sydney Raptor. Yeah, it's you can call it functional if it's chemically active. But you're really stretching the word function, and the word function doesn't have an accurate or specific meaning in biology and chemistry. It just does not.
When we use it in this context, we mean protein coding, but that doesn't mean that genes that don't code for proteins aren't functional. All, and at least in a colloquial sense, all genes are functional in that they at least replicate themselves. The question is if they do other things as well, like if they regulate how other genes are expressed, or if they code for a protein, or a couple of other things that certain sequences can do.
Yep. And if they replicate themselves, I would have to check, but I think it's exothermic. So, I mean, if anything does anything chemically in your cell, it's going to heat your cell up. And of course, cells, have to keep a certain amount of heat going on in order for the proteins to bounce around and do what they do. For us, it's about 98.
Are we talking about an exothermic reaction, a chemical change that gives off heat energy?
Yep. Yeah. Basically, and if there's some chemical activity, the thing is, if they add up the toxicity for the cell, then the cell naturally dies.
Yeah.
And that's natural selection at the level of cells, which, happens at cells too.
Totally.
But anyway, so this is ferritin, and that's kind of what we're going to explain. But I mean, this is one amino acid, so we're going to dig down a little bit deeper. And the other really important thing about this is if you get an idea.
So now we're drilling down from the secondary, tertiary structure level of the thing into the primary level of the structure.
Is what you're lower than that. Yeah, we're going to go down to atoms.
Lower than that. Okay.
So we're going down to carbon. Okay.
Oh, okay. We're getting real deep.
So we got carbon.
We're
right
going
here,
down
right.
to the molecular atomic structure, not even the microscopic
Yep.
structure.
Yep. And okay, here's our periodic chart. Okay, here's your transitional elements. Zinc is not considered a transitional element, but it's in there. But iron is a transitional element.
Zinc is a transition metal.
Well, so some people claim it's not because it's pretty close to having that shell filled. So,
Okay.
I don't know.
You know
Anyway,
what? I think
it doesn't matter.
There are a couple of unique, like kind of exceptions, wonky chemicals that don't exactly fit into the rules. Like polonium. Polonium is another example. I think it's listed as a it's listed as a metalloid, but it's debated whether or not it's actually a non-metal or a metalloid. There's a couple elements like that.
Yep. Hey, Breakfast Tacos is here.
Yeah,
so he must have been up all night too.
Oh man, he was. He's been working hard on his channel. Like he's really trying to make a go of it. I'm really hoping it pans out for him.
Yeah, it's working so good so far. He's got a wonderful channel. So anyway, so here's carbon. So up here we have carbon where my cursor is.
Yep.
And then
and
carbon then that is
it's a non-metal. It's got an atomic number of
in the
6.
middle.
So it's got a really balanced number of protons, electrons, and neutrons. It's got 6 of each of them. It's got 6 protons, at least the main element of carbon, not the isotopes. There's a lot of different isotopes that have different numbers of neutrons, but carbon 12, the one we're usually referring to when we talk about carbon, has 6 protons, 6 neutrons, 6 electrons. It's got the exact same number of all 3. And that makes it an extremely bondable element. It can form all kinds of fascinating, complex bonds. I think like you can bond up to like 80 different carbon atoms in different ways. Like there's a bunch of structures that are just made out of nothing but carbon bonding to other carbon atoms.
Yep. And so this is the carbon atom, and oh my goodness, I hate when it automatically switches over to erase when you tap a certain way. Anyway, so carbon atom has six protons, and it has 6 electrons. So 2 of the electrons are in the first shell, and this is a Bohr model, and that's called the S shell. And 4 of the electrons are out here. Well, this guy, the P shell,
and the Bohr model is something where it's like it's kind of been refuted a little bit, but we still use it because it's useful. It's not exactly right, but it is very useful.
It's a very accurate model, because quantum mechanics makes it happen. But anyway, so we have 4 electrons out here, and the thing is that this second shell likes to have 8 electrons. So it likes to have 8, and it doesn't. So what it's going to do is it's going to grab electrons from other atoms, basically. 4 of them. It wants 4. So it wants to be whole. Every good atom just wants to be whole. So that it's happy, like we want to be whole and happy.
Whole, we mean it's got all of the electron shells up to the outer shell are filled, and the outer shell itself is filled. And when that happens, that means the element, or the compound rather, is stable. Everything has a full outer shell of electrons, and therefore no reason to bond with any other chemicals or to break that chemical bond, because it's stabilized the atomic or the molecular nucleus.
And the very simple thing here is hydrogen has only 1 electron, and it's unhappy because the S shell likes to have 2 electrons. The next shell likes to have 8. So hydrogen's unhappy, so it's kind of reactive. So you'll have it combining with other things. But then the second element, which is
there's a couple of chemicals that are diatomic, and I think hydrogen is one of them. Diatomic means that it exists in a state such that you will never find just one atom of that element. You'll always find at least two. Oxygen is an example of another diatomic element. It's not stable as a single atom. It's only stable as two oxygen atoms. That's why oxygen is always written as O2.
So here's the inert gases: helium, neon, argon, krypton,
Yes, the
xenon,
noble gases.
radon.
Yeah.
What is OG? I forgot what that is. Oh, that's organoson. You don't see that often. But anyway, so these are really stable. But okay, going across here, we have lithium, which is a real bitch of a metal that will burn your hands off if you touch it. And that has only one electron, and beryllium has two electrons, and boron
lithium's an alkali metal, and alkali metals are extremely reactive.
I had
Sodium is one of the most reactive elements. If you take a block of pure sodium and you throw it onto a lake, it's like an instant explosion. The block gets launched into the sky by the explosion. There's a great video of a guy throwing a block of sodium onto a lake, so you can see the insane chemical reaction that an alkali metal has when it meets water. I think the alkali metals are extremely reactive, and the alkali earth metals, the category to the right of it, beryllium, magnesium, those are still fairly reactive, but just less extremely reactive than the alkali metals are.
Yeah, my Auntie Frances would have a video if they'd had video cameras back then. But in the 60s, we got stoned on acid, and I happened to have 2 pounds of pure sodium, and it was stored in kerosene. So when you
it reacts with the oxygen. It has to be stored that way. Yeah.
Right. So it had a white crust around it. So you take it out of the kerosene, and you take a butter knife and you cut a little piece off. It's like wax, and it's super shiny, and then it instantly fogs up. So we cut a bunch of pieces off, and we went around. We had a minnow pond, and we were throwing them in the minnow pond and causing these explosions. And my Auntie Frances was going to call the cops on us. And
you know what? If you can't cause explosions while studying chemistry, then what in the fuck is the point of studying chemistry? Frankly, it's like one of the coolest things you can do with chemistry. So,
well, in her defense, that wasn't the.
I refuse to accept that causing explosions isn't a perfectly valid use of chemistry. But anyways.
In her defense, we also fired up the John Deere, and we were doing popping wheelies with it. And we also started the greenhouse on fire. So on the same evening. And we also got the shotgun out. We got the shotgun out, and so.
This just keeps getting worse. Okay.
Oh, yeah. Okay.
I understand now. Your poor aunt. No, she
lived on the next
sodium
40.
is like that, and I believe cesium is also like that. That cesium is an element that has to be stored in like liquid containment so that it doesn't react to the oxygen and other chemicals in the air.
Yeah. So anyway, going across the table here, we have boron, which has 3 electrons, and so like it wants to grab either 5 or give. It's kind of in the middle. And then carbon, which is wonderful. Carbon is kind of right in the middle of that. It wants 4, or it would have to give up 4, but it usually picks up 4. And then nitrogen has 3, oxygen has 2. All of the halogens like chlorine, fluorine, bromine, iodine, they want 1. Basically, they'll grab 1. So sodium chloride would be this chlorine's combining with that sodium. The sodium is going to donate its electron to the 7 electrons that chlorine already has, and it'll get 8, and it'll be happy like argon. So argon is the happiest shit going on, and all these other things are,
the noble gases in general are very happy and stable. They
very
all
happy,
have
very happy.
a full shell of outer valence electrons, And as a result, they do not react to things very much. They do not bond with other things very much. They're very unreactive. That's why they're called noble. It's because they're too
So
the snooty chemicals that won't react to other chemicals. I'm too noble for you. Yeah.
this little group of 5 here, carbon, nitrogen, oxygen, phosphorus, and sulfur, are the most important thing in life. And then over here, we have sodium and potassium, which are also important.
Mhm.
And iron is important, and zinc. And there are about
Did you mention
24.
hydrogen?
What's that?
Did you mention
Oh,
hydrogen?
Nobody talks about hydrogen. It's too common. It's everywhere. We'll get into hydrogen in a little while.
So
But
basically, the funny thing is the 6 most common chemicals in living organisms: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. That's almost all of the nonmetals. The only nonmetal that doesn't make it in is selenium, and I'm pretty sure that exists in living organisms too.
yeah,
So it seems like
selenium's in trace amounts.
non-metals are like the chemicals that
These are
are
non-metals.
best for living structures.
Yeah. So anyway, so those make up the bulk, the bulk of our body. Hydrogen
That's
is kind of like,
nerdy joke, Sydney Raptor. I'm totally stealing that.
do you hear oxygen went on a date? Oh my god. Oh, that is good.
Because the chemical symbol of oxygen is O and the chemical symbol of potassium is K.
Yeah.
So,
Sydney, I think, can correct me if I get anything wrong here. So anyway, hydrogen is like the raccoon of the chemistry world. Nobody talks about hydrogen, so we don't care. But anyway, the thing about carbon is it's a tiny molecule. It's only got 2 shells, and it just happens to be perfectly positioned to give us the richest complexity, and that is why we have life, basically, because of carbon. So if you're looking for a god to worship, it would be carbon. So
yeah.
So anyway, if we have a carbon here, and we have I don't know what color to make hydrogen. Maybe I'll make hydrogen orange. So anyway, we got a carbon, and it will hook up to 4 hydrogens like that.
Mhm.
So this is a valence of 4, and that's pretty important.
That works perfectly for the carbon atom because it gets the 4 valence electrons it needs, and it works perfectly for each of the 4 hydrogen atoms because they each get the 1 valence electron they need, and now everything has a nice, stable, completely full outer shell of valence electrons, and everything's nice and stable and bonded. And yep, that's methane. Which is a very common organic chemical. We all have methane in us.
And this one basically is okay. So the reason we don't care about hydrogen, we don't even draw them anymore. We just put just pretend they're there.
Yeah.
So basically, we just have to draw the carbons. We know there are 3 hydrogens, hanging around here.
Yeah.
And this one is going to be ethane. Okay.
Yeah.
And then the third one, which is really cute, is propane, which everybody uses in their stove, I think. Well, some people anyway.
Yeah,
this would be propane.
Our favorite King of the Hill sells it and sell accessories for its usage. I sell propane and propane accessories.
Oh, I didn't know that. I'd forgotten.
You never watched King of the Hill? It's a great show.
I watched King of the Hill, but not for a long time.
Yeah,
So
Hank Hill, the main character, he works at Strickland Propane. That's his thing. He sells propane and propane accessories. And
cool.
he's so into it too. He's like always talking it up, how it's the superior heat source for grilling.
So this one is propane.
Yeah.
And the cool thing is we've got a carbon chain going out here, right? So we got 3 carbons. And the neat thing about the carbon chain,
you can take the methane structure and tessellate it, and it just gets longer and longer, and things still stay balanced because everything's getting the valence electrons it needs to have a stable, full outer shell.
Right, because carbon is in the middle, it will hook up to itself as well as other things. So that's the interesting thing about carbon being at the number 4 position out of the 8, shell of 8 or whatever. So that's pretty important. So then we have protein, and you would write that, okay, there's a C right here. So you'd write C, and you would write H, and then you would write 3 for the first one. And then C, all the ones in the middle are going to be CH2s, and you're going to have a CH3 on the end.
Mm-hmm.
So that's kind of the odd one out. So that's one way to write it. Now, another way to draw this
would be CH4, and then ethane would be CH3CH3.
Yep. Makes good sense. So
yeah, I'm starting to learn this stuff. They're learning me in school about this.
Yeah, they'll learn you up.
Yeah.
And CH4. Okay. So another way to draw this is that you'll see all the time is we'll just draw a crooked line or a zigzaggy line, and this is one carbon, and that's another carbon, and here's another carbon. Okay. So so that's a real simple way to draw it. So if I want to draw a big long one, basically I would go, forever. And some of these things are interesting, like carotene, and we'll may get into that at some point. That'd be 1, 2, 3, 4.
Another aspect of the structure of chemistry right now, aren't we, Mike? Are we getting into monomers and polymers? Is this kind of what we're looking at?
Not yet.
Okay. Okay.
Yep. Yeah, we're just getting into carbon chains, basically. So we have.
Okay.
So you can see how this came up here, basically.
Yeah.
But I mean, this is a long one. This I think this is triacontane, meaning it has 13 carbon atoms.
Yeesh.
I should have quit
it can basically, theoretically, just go on forever.
Yeah.
You can add more and more onto it, and it'll just stay stable, and it'll just get longer and longer. And one of the interesting things is at each stage, it'll have different properties. Like methane has slightly different properties from ethane. Methane and ethane both have slightly different properties from propane. As far as we can tell, the properties of a compound come from its atomic structure. So by manipulating its atomic structure, you end up with different properties. And
Right.
what that creates effectively for organic chemistry is a huge arsenal of chemicals that can do things for your body.
Yep. But it can do even more than that. Okay, this one is butane. Okay, butane has 4 carbon atoms, and butane gets its name from butter, actually.
Mm-hmm. Yeah.
Because rancid butter is butyric acid, which we'll show you in a little while. It's important that we talk about carboxylic acids at some point.
Mm-hmm.
But anyway, the point is when you get a chain of 4, we get a possibility now you could also have a carbon atom here, right?
Mm.
And you could have a carbon atom there, basically.
Mm-hmm.
So let's see, 1, 2, 3, 4, 5. So that would be 5, but I don't want to show you that yet because that would get into IUPC or PAC naming conventions, and we don't want to go there. Okay, so this one would be, now there's a methyl group, okay, methane. Oh shit, it did it to me again. Methane will form a methyl group if you take away 1 hydrogen, basically.
Mm-hmm.
And this is an ethyl group. And if you see all these big long names for chemicals, what we're doing, we take the longest chain, okay, which is going to be 4, and we'll call that butane. And then we'll look at this one and we'll call that a methyl group. And then we'll start numbering from the place where it gives the numbers the smallest, we get the smallest numbers. So we'll end up with 2-methyl butane. Okay, and that's where these really long, intimidating names come from.
Yeah.
But basically, there's something called the IUPAC naming conventions. Professor Dave has 3 videos on it, and they're wonderful. And he explains all of it, basically. So,
if there's one thing that can be very intimidating to people trying to learn chemistry, it's how freaking complicated the nomenclature is. Tricarboxylic acid is not an easy. Try and say that. 8 times fast, tricarboxylic acid, the names of things can be so complex. That is why chemical symbols are so helpful, and the nomenclature it can be challenging for sure. It's like they're trying to summon a demon with some of these names that they give different chemicals. But like you said, it's just the way the system works, where we're naming the compound after all of the ingredients and kind of the basic structure and the number of atoms that are in it.
Yep. And the neat thing about it is you can go on forever and create these extremely complex little monsters.
Yeah.
And the complexity of just carbon alone, carbon and hydrogen alone, gets incredible. So,
and that's how we get so many different compounds in our body that can do different things. We get proteins that can build cells. We get enzymes that can dissolve and catalyze reactions. We got, all these other chemicals, compounds that can do things at the cellular level, at the microscopic level. And then from the macroscopic level, we have chemicals that can break down our food and perform chemosynthesis so that we don't have to be autotrophs. We can get energy that keeps our internal system ordered and consistent through eating autotrophs and getting the energy that they made in their bodies into our bodies.
Yep.
Yeah.
And then
all of life is chemistry. Nobody can point to anything that living things do that isn't caused by chemistry.
Yep. And now the other thing you can do is you can take one of these hydrogens right here. Did it to me again? I got to figure out how to shut that off. You can take one of these hydrogens right here, and you can hook it all the way around to this carbon right here and form a ring. And so that forms
carbon
something called cyclohexane, basically.
These things are so cool. Like if you ever get some of those magnet toys where it's like little orb magnets and then little rod magnets, and you can build structures out of them. They look exactly like what we think carbon rings and stuff like this looks like.
Yeah. And that's a cool thing. If you've ever gotten one of those toy kits or Legos, you realize, oh my God, what did I do? You realize that the complexity grows just like with six Lego blocks, the ones with the 6 dots on them. Mm-hmm. I think it's just a tremendous amount of combinations that you can have with just 6 of them.
100%.
I forget how many it is, but it's a lot.
It's a factorial equation. It's an exponential increase in possible combinations for each factor you introduce. Every time you increase the number of factors by even 1, it's a factorial increase in the total number of combinations. And what I mean by factorial is it's a sequential pattern used for numerical calculations where you're literally just adding integers up in a sequential order. 1 + 2 + 3 + 4 + 5. And what we're doing when we're introducing new elements in a situation like this is we're saying that you're actually multiplying it by the sum of a certain factorial number, the number of the element you just introduced. So if it's the 7th element you introduced, the factor that you're multiplying by would be 7 + 6 + 5 + 4 + 3 + 2 + 1. And you can see how that can get really big really fast.
Yeah, so Sydney says this is why carbon does this easier. Silicon has an extra shell, so it becomes a little more complicated, and it doesn't quite combine as easily as carbon does with things.
Silicon is also a non-metal, which means that it can have conductive properties, which are not a non-metal. Silicon is a metalloid. It's something that's sometimes has metal-like properties, sometimes has non-metal-like properties. It seems that most living systems that we know about prefer non-metals as a basis. Carbon is solidly a non-metal. and it's not a very good conductor. It's interesting because we do conduct electricity through our system a little bit. So you might think, we need conductors, but we get enough of like iron and other like trace amounts of transition metals in our bodies that we can still do some conduction, enough conduction that our nervous system works okay.
Yep. So the other thing that you can do with carbon, which is kind of cool, is we can get rid of these two hydrogens here, and we can add a double bond, basically.
Oh, yeah.
Let's see.
Yeah.
So we got a double bond here, and that becomes ethene. We get rid of the A, and we call it ethene, and these are called alkenes instead of alkanes. So we put a double bond there, or you put a double bond here. And
can you refresh me real quick, Mike? A double bond is, I know this, but it's like blank. I'm blanking on it right now. What's a double bond again?
Instead of just one electron being shared between the two carbons, we have two electrons.
They're sharing two, right?
So there's two electrons.
Thank you.
Yep.
Thank you.
And if we get rid of another one over here, we cross those out, and we put three bonds. We have a acetylene gas, right? Yeah. That has three bonds, and that burns very, very hot, that sort of thing.
Mm-hmm.
So, and I'm going to forget things because I've learned and forgotten organic chemistry 4 times in my life. So bear with me.
No,
anyway, so we can have.
You've been pretty much spot on in everything you've said so far. It sounds like what my professors would say. I haven't heard anything that disagrees with that.
Yep. So we have so we can have 1, 2, and 3 bonds commonly between molecules. In life, 2 bonds is pretty common, but so that further complicates things. We just take away hydrogen and add another carbon, and so you can end up with all kinds of structures. Now, if we get down to this one, cyclohexane, which I believe has like 2 hydrogens on every carbon, but we go down to just 1 hydrogen on every carbon, and we put a double bond there, and a double bond there, and a double bond there. Okay. Now we have benzene, which everybody's heard of. I don't know why, but we have. Anyway, so benzene, because you don't drink a lot of benzene, but
no.
But anyway, yeah. And then there's
John, benzene in the jets.
Oh, there you go. Benzene in the jets, right? Okay, so. Okay, so
there needs to be more songs
about this stuff as me. Then a mnemonic device comes in handy.
Yeah.
Yes.
There should be more songs about chemistry, but it's hard to do because so many of the words have so many syllables in them. They don't fit a lot of melodic schemes for like tempo and stuff.
Yep.
But I've managed to make a couple. Like I made a little song about the tricarboxylic acid cycle to help me remember how it works for a bio exam I took.
Oh no. I know an amazing.
I won't sing it. Don't worry about it, Mike. I won't torture you with that.
I know amazingly little about biochemistry. More about molecular biology, but a little bit of
that guy that played Foxy on the old TV series Happy Days back in the 70s. Ensign Williams.
Oh yeah.
Maybe he could write a song about carbon chains or
or whatever. Yep. Okay, so now we can erase. We can go a little bit further now that we've seen that carbon chains can become extremely complex. Creating trillions, quadrillions of different molecules, different small molecules. We can go a little bit further and we can knock one of these carbons off and we can add an oxygen, okay? Well, oxygen ain't going to be happy until you give it 2 things, so we're going to have to put a hydrogen out here, okay?
Yeah.
And if we do that, you have methanol. Which is wood alcohol, which will make you blind, kids. Don't drink wood alcohol. Mm-hmm. Drink this stuff over here. So put an oxygen on ethane and an OH, and you'll have ethanol. So that's ethanol. And that is the alcohol that y'all love so much. And it doesn't agree with me. And this is propanol right here. And then we have butanol and what else? Yeah, that's about it. So now we have that, right? But you can also, let me see here. Formic acid is 1, 2, 3. Let's see. 1, 2. So I'm going to take 2 hydrogens off. Now, if I now you can also create another compound called formic acid, which involves knocking off a couple of hydrogens and adding something that oxygen can also do with carbon is give it 2 bonds. You can give it 2 electrons, right? And you can add an oxygen right there with 2 electrons. This one is only sharing 1 electron, so it's got to grab a hydrogen over here. And that's called formic acid or methanoic acid. So it'd be methanoic. So you always want to, it's very annoying. You want to say anoic, okay? Ethanoic, propanoic, whatever. So this is formic acid, which I believe ants give you when they bite you. So that would be
true. That's correct. Not only is that the case, there's an interesting behavior in ornithological organisms in bird species called anting, where when they have an injury or an infection or something, they will go stand in ant hills and let the ants crawl on them and bite them, because the ant bite puts formic acid into their body, which helps soothe their pain and promote healing. It's really fascinating.
no shit. What is that called?
It's called anting. Look it up.
Anting. Oh my god.
Anting. Yep.
So if I do that, it'll cure my headache?
I don't know. I don't know if it's like some specific way that the formic acid interacts with the bird. It might.
Well, we got a fire anthill out here. Next time my back hurts, I'm going to go out there. And,
yeah, there you go.
I'm going to take your advice. I'm going to take your advice.
Yep.
Okay. So we have.
You heard it here first. Scientific origins, according to Austin Sims, says go out and stand in an anthill. That's totally what I said. Yeah.
So we're still drawing our hydrogens, but we're going to quit drawing them pretty quick. We're just going to assume that carbon is always going to grab up enough hydrogen so that it has 4 bonds.
Mm-hmm.
And that's what you want to do. So, but for now, we're going to have them because it gets to be a pain in the ass to erase them like that. Oh, and I made a mistake. I did badly. Let's see, did I erase that? Okay, I want to get back to my little eraser. There, little eraser. So now what I want to do is I want to add another doubly bonded oxygen to my alcohol. So if I have ethanol, okay, so ethanol, right here, I have a good glass of wine. I leave the wine out too long, it turns into vinegar. So this is acetic acid. So this is acetic acid or vinegar, basically. Okay, you see what we're doing here?
Yeah.
Okay.
So what's interesting is, I think I'm imagining that acetic acid is really it's because it sounds like it's similar to acetyl-CoA. I'm assuming that acetyl-CoA is some kind of acetic compound because it's got that root acete in there.
Yeah, it's got an acetyl group in it.
Yeah, and acetyl-CoA is one of the it's the molecule that drives the carboxylic acid cycle, the chemosynthetic catalysis from which we get energy from our food. It starts off with 2 carbon molecule acetyl-CoA, which is derived primarily from the breakdown of glucose in glycolysis and pyruvate oxidation. Those are the steps that come before the tricarboxylic acid cycle begins, and fatty acids, beta oxidation. And then the cycle's goal is to complete the oxidation of the acetyl group and end up producing from acetyl-CoA to carbon dioxide, CO2. And in the process, it also produces ATP, which is the cellular energy currency. It's what our cells run based on. Actually, I think the majority of the ATP is created in the step that comes after the tricarboxylic acid cycle, something called the ETC, the electron transport chain. But I think it's it's another example of how these chemicals are useful for our body. In this case, these chemicals are useful for helping our body turn food into usable energy for our cells.
Yeah, this is the acetyl group over here, right here on the edge. For some reason, over here it's got 1 carbon, 2 carbons, and it's got that O group. So that's an acetyl group, basically, or an acetyl. I believe I would have to check. And then we got sulfur, nitrogen, which you can also hook up to these carbon things. Sulfur will grab 2 things. It's right under oxygen. Nitrogen likes to grab 3 things, so it's got a hydrogen and 2 carbons that it's hooked up to. There's another double bonded oxygen, another nitrogen, another double bonded oxygen. Here we have a phosphate group.
So this diagram, for anyone who doesn't understand, each of the letters represents an atom. When the letters are squished together like that, you're looking at a compound that has those 2 atoms in it. The 1 line drawn between things represents that they're sharing a single electron. 2 lines represent that they're sharing 2 electrons. There are a few symbols here I'm not familiar with. Like, what are those wide triangle-y lines? What does that represent?
Oh, that shows you stereochemistry. That means the oxygen is coming toward you out of the paper. Okay. Yeah, and the other ones are going away from you.
What is that little symbol like over by that pentagonal? It looks like down that. What are those 3 little lines between the bottom of the pentagon and O and OH there? Do you see those? You're real close. What are those?
Those go the other way. Those go, I believe. Okay. Yeah, I believe those go inward. Yeah. So that's kind of a weird way to put it.
To know how to read the chart, because what we're actually being shown here is a really complex chemical structure.
Yeah. But something
James Tour would doodle on his blackboard and then scream, "You can't show me how! Show me!"
Right.
Mr. Farina!
The thing you want to notice here is that these little vertices right here, that's 1 carbon atom. Here's another. Okay, at the end of the line, there's another carbon, another carbon. We just don't draw the carbons and we don't draw all the hydrogens. Because if we did, this would be a fucking mess.
Yeah.
So anyway, here's a carbon, here's a carbon, here's a carbon hooked to the oxygen. And that's the way that works. Okay. So now we've got 2 carboxylic acids, which and I got a messy drawing. It's pretty messy, pretty messy. I don't know.
It's good enough for our purposes. I'm learning, Professor Mike. Keep spitting, keep cooking.
Okay. So let's see. Let's go a little bit further here with we want a black one. So we got a C and we got a C, and then we have a double O and we have an OH, right? Now, another thing we can do with carbon is we can draw a C and a C, and we can hook a nitrogen up to it, right? 1 time. But then we're going to need 2 H's, which we're going to draw like this, H2, okay? And that is your simplest amine. So that's an amine, basically, with nitrogens instead of oxygens. Oxygen only needs 2 things, so it's got 2 bonds. Nitrogen always wants 3 electrons, so it's got 3 bonds. So this is an amine.
What I would recommend for the audience to get the most out of this video, if you're watching this live, just write down the names of all these chemical groups, and then when we're done with the video, go on Google and look them up and see what their properties are, like see their melting point and their reactivity and all those things that talk about the properties of the specific compounds, and you'll learn how they fit into the overall puzzle of biochemistry. If you're one of the people who's watching this after it's recorded, even better, you can just pause the video now, go to Google, look up amine, and find out, what Mike's talking about.
Yeah, and this one is called ethylamine because that's ethyl ethane two. So it's ethylamine. And amines are interesting. Carboxylic acids will they'll burn your tongue a little bit. They'll sting your tongue like vinegar.
Mm-hmm.
They have an acidic property.
That's basically what acid means. It means it has a pH. It dissolves things that are non-basic, and when met with a base, it neutralizes.
Yeah, and I forget what the
and pH is like one of the most important things in biology. There's a bunch of chemical reactions that will not occur at the right pH. A lot of them involving enzymes. Like enzymes denature at a certain pH. They dissolve. They become no longer enzymes. They become like a soupy mass of amino acids instead of an enzyme, and then they can't catalyze anything. And that is why pH is so important in biochemistry.
Yep. And we take a carbon and we hook one nitrogen to it. Basically, let me see here. We could hook one nitrogen to it, and these things are fishy smelly, right? But the smell in fish is this.
Yeah.
Basically, it's trimethylamine. These all have, the hydrogens on them. Mm-hmm. So these are CH3 groups, and that's what makes fish smell so bad. They have a lot of this thing.
As the old saying goes, chemistry is smelly, biology is all about icky, squishy things, and physics rules.
Yeah. Right. So we have an amine and we have a acetic acid right here. So acetic acid and an amine, and that's a carboxylic group basically. And if we combine these two things, oh my God, I just went small. Combine these two things and we go C double O. This is now I got acetic acid, right? Mm-hmm. But instead I'm going to put a nitrogen over here with two hydrogens on it, and I'm going to call it an amino acid. So that's your amino acid. Mm-hmm. So this is glycine. This is the simplest amino acid called glycine, basically. Mm-hmm. Okay. And we can take this simple. I'm going to show you some pictures here next because it's going to be a lot neater.
I never knew the etymology of amino in amino acid. It comes from amine, huh? That's fascinating. Amine, yeah, I didn't know that.
Yeah, what is the etiology of amine? I forget. Let's see. Etymology. That's what I want. Etiology would be the cause of my cancers. Let's see. Where are we? Entomology, etiology, and etymology are tough. Yeah. Okay, am is from ammonia, and en is just en means what is it? Enos? I think it means a little, or I don't know. Used in chemistry, it means Greek something. Enos. I don't know. It doesn't tell you what it means in Greek.
It sounds like it's diminutive. It's like ito in Spanish. You don't say just mijo. You say mi ito, mi hito. Not my son, my little son. It's like a term of endearment. Only here is being used as a suffix to, I think, probably to indicate that we're not talking about a macromolecule, that we're talking about just a molecule.
A part, yeah. And something generic. Anyway, this is ammonia. So, instead of a carbon here, I have hydrogen, right? So we have ammonia. So anyway, so that's the first amino acid. The other amino acids just add to this right here, except for proline, which is a little different. We'll show you that. Basically,
hold on. What is that one called again?
Oh, I'm sorry, I put it in the wrong. Hang on a second. I screwed up. I made a mistake. Okay. So this is glycine. That's
Ethylamine is the simplest amino acid. You
amino
said
acid. Yep.
is
Yep.
ethylamine, and now you're talking about other amino.
Oh no,
acids.
no. Ethylamine is this guy up here.
Yeah. And then the one below it, what's that one called?
This is vinegar. The one below it is glycine.
Glycine.
So
Glycine is the simplest amino acid, and you're telling me that every other amino acid has the basic structure of glycine at the core, and then it's just modified.
Yep, and I'll show you how it's modified.
I didn't know that either. That's super freaking cool. So that makes amino acids like way easier to make than I thought they were.
Oh yeah, they're pretty easy to make. They're pretty common, and there were hundreds of different kinds of amino acids. But something else we like to do in chemistry is just draw like just the vertices, whatever, and maybe draw the double bonds. But then we like to use an R basically to represent some big alkane or some other group. So there's something else out here that could be a CCC. There could be isopropyl, or it could be anything basically. So we represent it with an R. So we'll put an R there. So when we create the other amino acids, you're going to see it often represented as an R, meaning that this is yet to be defined. We're going to tell you what it is later. Okay. So there's no echinidal acids, unfortunately, nerdy. Sorry. Scott, are you paying attention? Did Scott leave us? Where the fuck did he go? Oh, no, Scott's here. Okay. Scott, I hope you're paying attention to chat and you're not sleeping. Scott, are you sleeping?
I am definitely not sleeping. There's no sleeping going on here.
Are you paying attention to chat in case we get any? Okay.
Yes,
anyway.
I am paying attention to chat.
I think the subject of this video is so dry and boring that the trolls aren't even bothering.
Everybody's going to sleep, right? Yeah, that's a problem.
We're
Okay,
pretty good chemistry reactions and some pretty sharp chemistry jokes. So the nerdy jokes are really going on out here. And I think
we want to see those. We want to see those. Yeah, I can't draw anime. I'm sorry. Anime. Can't draw an anime. So what I have here is an R, and we're going to replace the R with something. And the something, this one, remember, is methane or methyl. So that's called CH3, right? Mm-hmm. So that's a methyl group. And if we put a methyl group here with its associated hydrogens, we have something called alanine, which is the A amino acid. So we have alanine. So that's your next example.
One of these is going to be basic.
Hold on. Yeah, I did it right. Okay.
Well, is one of these or some combination of these? They're going to be the start and stop codons in the genome, right?
Methionine.
Yeah.
Yep. And I can show you that one in a minute here. But okay, so we have alanine. Let me erase. Oh my goodness. What did I do? Oh no, I did something
for
horrible.
Anybody in the audience who doesn't know what I mean when I say that, in your genome, you have a bunch of base pairs that they produce proteins, and then you have a bunch of base pairs that they don't produce proteins. They either only replicate themselves, or they replicate themselves and they do some other thing, like they impact how another part of the genome is expressed. When I say a start and stop codon, the start codon is a protein sequence, or an amino acid sequence rather, that causes the base pairs after that sequence to actually code a protein. And then the stop one is the sequence that tells them to stop doing that, basically. Is that correct, Mike? You think that's a good definition?
Yeah. Start codon and stop codon, but we're nowhere near that stuff yet.
Yeah, fair enough.
Okay, so here's our amino acid, and we got these groups. So if I have a methyl group right here, it's an alanine. If I have one carbon and then two more carbons here, like in a little tree, okay,
Mhm.
then I've got valine, which is a V. So that's valine, and they all build up from there. And I'm going to show them to you now. So anyway, amino acids just change this R.
Wait. So let me check for clarity right now. You're saying glycine is the most simple amino acid, and then every other amino acid is built on it's a more complex structure, but at the core of the structure is glycine. And as you add on to glycine, eventually you get to this V compound.
Yeah, that's valine. Yeah.
Valine, and every other amino acid from there is some kind of valine.
No.
Or that it has the structure of valine at the root, or some variation of that valine structure.
Okay, all we're doing here is we've got the amino acid structure, which with nothing here. If we chop all this off, right? We have nothing. Then we have glycine. That's the simplest one. It's just got a hydrogen. So R equals hydrogen. Okay. For glycine.
Okay.
R equals H. Okay.
Right. Okay. Gotcha.
Yep. For
and
alanine.
In the case of valine, R equals C. Yeah, okay. I'm understanding now. Okay.
R
cool.
Equals C. Let me see here. C. Oh God. I forgot how to write it. God damn it. I don't know. It doesn't matter. Fuck it. Anyway,
yeah, no, I get the point you're making.
Okay, so all amino acids are just going to change this R structure here.
Yeah.
What in the fuck?
Okay, so I do understand.
Yep.
Or at least I think I do.
Okay. So anyway, now I can show you some pictures. And I'm going to have to go through a lot of pictures in order to find the right ones because I didn't put them in any order. Let's see here. Okay. Yeah, we don't want to do that. I'll go back one. Okay, so let's see here. We'll find the right pictures. Oh, here's a picture of something that's going to be important. Oh, here's a picture of all the amino acids. These are other groups that you can create, right? Like we got the carboxyl group, carboxylic acid right here. And then we have acid anhydrides, ketones, aldehydes, ethers, alcohols, haloalkanes, arenes, epoxides, amines right here. Here's your amine. Basically, you have, we won't get into the different kinds of amines. Amide, which is a kind of a combination between, it's got a double O and it's got an NH2. And so you can look this up under functional groups in the Wikipedia, and it'll show you a whole bunch of these things. These are just a whole bunch of stuff.
If you're watching the replay, just hit the pause button and check it out. Which, if you're watching the replay, shout out, give us a like and a subscribe. We should say that at least once on the stream, right?
Yep. Okay.
And one thing I think you're probably realizing here, as me and Mike are talking, is that a lot of understanding chemistry is just a ton of rote memorization. You're memorizing all the chemicals on elements on the periodic table. You're memorizing all the chemical groups and periods, the different families of chemicals. And how we organize them into different types of chemicals. Then you're learning about all the different kinds of compounds and memorizing big lists of those, like the big picture of amino acids and carboxyl groups Mike just showed us. A lot of chemistry is like just memorizing as much as you can of huge sets of, information, chemicals, compounds, and groups of chemicals and compounds.
Yeah, but none of you want to do that. What you want to take away from this is that carbon is like a Lego, and you can make these very complicated structures with it. And when you see these big, intimidating structures, with the little lines, all the lines in the vertices, and they're
Yeah.
pointing off. Every one of those little vertices has a carbon on it, and all the rest of them, they'll show you the nitrogen, they'll show you the phosphorus, and you can decode any structure by just looking at how it's put together, and just think about how you would put Legos together, and what you would do with that. These are all the amino.
We know this because we've spent centuries now studying chemicals and learning how to purify and refine them into the base elements that form them by using chemistry to separate things until they can't be separated anymore. That's basically what the table of elements is. It's all the chemicals we found by separating atoms of different types in molecules until they just can't be separated anymore. And what we found out is that they follow this pattern of numbers of protons in the nucleus and changes in chemical properties as that number increases through a series of types of elements. Your nonmetals, your alkali metals, your alkali earth metals, transition metals, semi-metals, nonmetals, basic metals, halogens, etc.
Yep. But don't be intimidated by this shit. Now, this is just these pictures here. Okay.
A little intimidating at first, but once you start to learn more about it, it gets less and less intimidating.
Yeah. There's just carbons here, at these little at these little points, right? These are called heterocyclic
This
compounds.
is kind of what T. Savo was talking to us about, is molecular geometry.
Mm-hmm.
They all form a shape based on the valence electrons they share. We're seeing a lot of hexagons here, for instance.
Yep. And pentagons. Okay, this is a pyrosol. These heterocyclic compounds are just different combinations. This one has sulfur stuck in the middle of the ring. This one has oxygen. This has nitrogen. Okay, down here you have a pyrite.
That's pyrrole?
Pyrrole, yeah.
I wonder if that's similar to pyruvate.
I think it's derived. I'd have to look. I can't remember pyruvate.
Probably.
Anyway, and down here we have pyrimidine. And here we have purine. And purine is the A and the G of nucleic acids, right? They have a purine ring.
Adenine and guanine?
Yep.
Oh, so purine is the nitrogenous base? Yeah. So
this one is there's a little
DNA, more. What you have are base pairs that are nitrogenous compounds bonded to a phosphate group, which is usually pentagonal, and it's all laid out on a ribose, which is a kind of sugar backbone, which is the double helix. So the double helix, the sugar backbone is the double helix in the DNA drawing, and then the base pairs in a drawing of a DNA are the lines you put between the double helix. And while we sometimes draw them as solid lines, what they actually are two segments that are bonded in the middle, usually by a hydrogen bond, I think.
Okay, so pyrimidines and purines, but you have all kinds of other things like indole, which is blue. Like some of these are really bright colored dyes. Xanthine, I think, is involved in why leaves turn orange and beautiful colors in the fall. And all of these things are really, really stable ring compounds. They'll say, the fossils can't possibly have these things in them. Yeah, they fucking can, because coal does too. And these things last for millions and millions of years because they're very, very, they're well hooked up. They're very stable compounds. But it all starts there, basically. So those are the different heterocyclic compounds, they call them. Hetero meaning different, and cycle. So hetero means that it doesn't just have carbon atoms in it. It has like nitrogens and sulfurs and all of that stuff. So anyway.
Yeah, I know you kind of went past this already, but I do really think that color is a really interesting property of matter, because what it actually is it means that matter has the property that it absorbs every frequency of wavelength of light except the one that gives off the color that we call it that color. It's really interesting to me.
Here's carbazole here. Somebody was asking about carbazole.
Yeah, Nerdy wrote and asked about it.
Yeah, I can't make it any bigger. Damn it. I'm at the max. Anyway, so that just shows you how complicated it can get, right?
It can get complicated, indeed.
Can get complicated. We're going to get back to amino acids here. Oh, my thumbnail is basically...
This just screams uncomplicated, Mike. This is real simple.
This is just a bunch of... This is a bunch of...
insane 3D puzzle I ever tried to put together.
These are just proteins. These are different proteins. Yeah. Okay.
And so proteins and what RNA they do molecule. Is basically defined by their shape. And we're looking at a bunch of different shapes of proteins that'll all serve all kinds of different functions. Maybe some of them serve similar functions. I'm guessing some of these are enzymes. Some are proteins. What else are we looking at?
Enzymes are all proteins.
Yeah. Enzyme is a kind of it's a class of protein that helps catalyze chemical reactions.
Some reaction.
Because its shape, it has what's called an activation area on its surface. It's a little divot that provides a very efficient space for chemical reactions to occur within, and that's how it accelerates chemical reactions.
Yeah. Parvalbumin binds, it kind of stores calcium and holds it. So there's...
Look at that one. That one looks kind of like a square donut. What is that one? Glycolate oxidase?
Glycolate oxidase.
That's cool. So I wonder if that's little square there, if that's an enzyme, and that little square in the middle is the activation space.
Usually that's what happens, the activation. Yeah. Well, we'll get into that later, basically. Okay. Calcium binding parvalbumin is parvalbumin. I showed the other day, I was showing a picture of that, I think. Anyway, but that's just how they fold up and the interesting shapes they have.
It's funny to think. Go. Can you go back real quick to the diagram? Okay. It's funny to think that these are the Legos that build your body.
Yeah.
If humans were a Lego statue, the Lego bucket you got would be full of these things. Yeah. And then the blueprint, the little booklet that shows you how to build the Lego pieces in the bucket into the statue you want them to be, that's our genome. That's our genetic code. Super cool.
We haven't quite gotten to that part yet, but anyway, this is a picture of what like if you were to this is still a cartoon picture, but this is how packed these proteins are inside your cells. I mean, there's a little bit of water in between them, and these are, cell membrane. There's a flagella.
Well, it's important to remember that this looks very packed from our perspective, but in fact, atoms are mostly empty space. So as packed as this looks, it is still actually mostly empty space.
Atoms aren't really empty space. I'll argue with you on that.
Yeah, fair enough.
They're fields, basically. They're pretty solid.
Yeah.
Anyway, let's see. Where are we? Those are the amino.
There's a lot of the structure of an atom that isn't actually a particle occupying space. Like the electrons themselves are really, really small, and they orbit around the atom, and they produce the magnetic field, like you said. And there's a nucleus in the atom, but both of those are really small.
Yeah, at that level, there isn't really such a thing as particles and waves and stuff like that. It's something that we have trouble comprehending. But so basically, it's a field. The whole atom is like a hybrid field with the protons, neutrons, and electrons. Anyway, okay, we're back to amino acids now. Now, you remember glycine right here? You see the H? Okay. Your R equals
this
H.
is a really cool chart.
Right. Alanine, R equals CH3.
Yeah.
Okay. Valine, R equals CH, hooked to two different CH3s. Cysteine,
so
which is really
cool.
important, has a carbon and then a sulfur. So that's what makes your hair curl, cysteine. Those two sulfur, if you have two of these next to each other, they will hook up and they'll fold the protein in a certain way. So what you do when you curl your hair is you dissolve those bonds and then you let them reform somewhere else and closer together, and it will curl your hair. So that's how hair curls. Now, proline is a kind of an odd man out because look at this sucker. Okay, it's got an R here, but it hooks back up to that nitrogen, and that makes protein a alpha helix killer and a beta sheet killer. But we're not ready to get into that yet. But anyway, and here we have leucine, which is a little kind of like valine, except it's got another carbon stuck in there. That's leucine. Isoleucine is just a different form of leucine. Carbons are arranged differently. Okay. And here's methionine. That's your start amino acid usually. The beginning of any protein. It has two CHs and then it has an S. Kind of like this one up here, except it also has another CH after it. So it's a little bit different.
This is what triggers the conversion from interons to exons, right?
Yep. Well, yeah.
Scott says
no.
That's different. I get that backwards. My bad.
That's different. Okay, this is what starts the protein. Basically, the protein creation. It scans the genome until it finds a certain codon, and then it'll stick a methionine there, and then from there on it goes on. And then we got tryptophan, the turkey, the turkey drug, that makes you sleepy. Phenylalanine, which is a little more complicated. It's got a ring in it, and these are kind of like bulky, right? And then we get down here to where we have hydroxy groups like alcohol, and these are polar. These are going to be a little bit sticky and magnetic.
Yes, that's what polar means, you guys. It means it's ionic. It means there's a slight imbalance between the charge of the neutron and the charge of the orbital electrons. So it's either slightly positive or slightly negative, which means it attracts attracts the opposite slightly positive charge. Like if you got a slightly positive ion, it'll attract a negative ion and they'll form an ionic bond where they're held by the magnetic attraction of their opposite electromagnetic forces. And if you've got two ions of the same charge, they repel each other, just like a magnet would if you put two magnets with the positive poles towards each other, they repel each other.
These things help. These things help. These like water. Water will stick to these, so these are hydrophilic, and these are hydrophobic. So these guys are all hydrophobic. They form the inner core of most proteins, and this is why proteins fold, because this likes water. This fucking hates water. It just hates it like like a desert frog. We come over here and we have charges. Basically, this would be a positive charge, which means it's basic. And these are bases, and you can see it's got a butane chain in it, four C's, and then it's got a amine group at the end of it. So it's got two amine groups, one there, one there. That is lysine, or K. Okay, and this is arginine, which has 3 nitrogen or amine groups in it, basically. We won't get into tertiary amines, but that is what that is. This one, histidine, is a little more complicated. And then we get down here to the negative charges, or the acids, right? We have glutamic acid. You'll say E. It's actually glutamic acid, but if you pronounce it glutamic acid, you'll understand that it's an E. And if you pronounce, and don't say aspartic acid, like a wood tick, say aspartic acid, like damn, and that's a D. So aspartic acid. But look at this little sucker. You see that right there? That's vinegar, right? So the R is equal to acetic acid, and you have aspartic acid. Okay.
That is so fucking cool, Mike. Yeah,
Yep,
no,
this is
Scott said this chart is off the chart. It absolutely is. And you know what I think is really cool about it? This reminds me of like the expanded form of a stem and leaf plot. You have
yeah.
the stem, and then all the leaves are the things that are highlighted with colors. That's so fucking cool. I had no idea that that's how amino acids actually worked in terms of their chemical structure. This is blowing my freaking mind right now. This is awesome.
This is why we're doing this, right?
So cool.
Anyway, you can see like, okay, the 4 basic types of amino acids, right? But then I'm going to go back to another thing and show you this one, okay, which shows you different sets, overlapping sets. So we have small amino acids, we have polar amino acids, we have hydrophobic, essential amino acids, which they have a line drawn around. We have the negative ones, which are the aspartic acid and glutamic acid. We have glycine out here.
These terms, these adjectives that we're throwing on here, these are just describing like their properties and how they behave, right? Like hydrophobic describes that it withdraws from water. Polar means that, it's got a magnetic charge. It's attractive to the opposite charge and repulsive to the same charge. I'm not sure what all of them mean, but another great. So we're going over a lot of information in this video. If you're somebody watching and trying to learn, do make ample use of that pause button and look up some of these things. That is cool.
So
okay,
what this shows you is that with these 20 amino acids, we have all of these different overlapping properties, and that all combines with the complexity of biology, and that allows the Legos to have a lot of character, so that you can create a lot of different machines.
Yes, this can also give us a roadmap as to how they're likely to fold.
There's a whole lot when you get to that part.
Yeah.
Okay. Anyway, so that shows you that we have this rich set of Legos that you can put together, thousands of them together, and create all of these immensely different proteins or molecules that do different things, depending on how you put them together. And what the creationists want you to think is that these proteins have to be like these finely tuned machines. They don't. Okay, there are many proteins that will do exactly the same function. There are probably millions of them that will do the same function, basically.
If one protein won't work in a system, another one probably will.
Yeah. Okay, that's an RNA.
They evolve like everything else.
Yep.
Selection
and here's just
them too.
So if you look up amino acid on Google and click images, you'll see these charts, and you'll be able to get them for yourself. They all come up. Here's
and it's still the basic stem and leaf plot thing. That's so fucking cool. I didn't know that. That's cool.
These are very useful. Okay, so now we're going to get into something. Okay, this is
shit.
Yep.
Oh gosh.
This is 2.5 amino acids. Okay, basically this is a protein. So what happens? Let me go back. Let me go back over here and draw you a couple proteins. So let me see here. So we got an NH2. Okay, so we got an NH2 there. Well, no, we don't want to draw that part. Excuse me. God damn it. Go away.
You're excused, Mike. Just don't let it happen again.
Okay, so here we have a simple, basically, amino acid structure. Okay, we have an O, and we have an O, and then we have an H there. Okay, it's going to be an H, right? And then over here, we have another one. So we have an O. We'll draw the H on that one. We'll draw the NH2 over here, and then we'll draw a C. Basically, let's see. Okay, C, O, another C, another NH2. Okay. This is the order that we read these in are N to O. So from here to here, okay, that's the N terminal to the C terminal. This is the C terminal end. This is the N terminal end of the protein, right? So we got a protein like that. So what we do here is we're going to grab these two hydrogens and we're going to grab that hydrogen, or let's see, I think we want one hydrogen, and we're going to grab that OH right there. And we're going to take out water. We're going to dehydrogenate that sucker. And when we do that, oh my goodness, Daddy fucked up again, as I often do. Okay, I'm going to take that, and we're going to take that. So we're going to take water out of that. And now what we have is a protein, or we have a peptide. Basically, it's a diamino acid.
Okay, so if you drew this as a chemical equation, you would have the formula you started with on the left and the formula you started with on the right, with like a plus sign in between them, and then there'd be an arrow, and at the end of it, there'd be H2O and this final structure.
Yeah. So this would be, this would be diglycine, basically. It'd be two glycines together, because we don't have any R groups down here. I drew the R group. Okay, we have R groups here and an R group here. So these are two different amino acids. But in this case, we're going to hook up two glycines where R equals H. Okay. And that's how proteins are formed. And then this one over here, this OH over here, will hook up to another N, two more C's, another N. So anyway, what it looks like is CC, N, CC, N, CC, N. And that is a protein. Basically, these amino acids hook up.
Okay. Yeah, absolutely. And what I'm noticing is that this is extremely possible. It's supremely possible. It's like creationists often like represent this as if the odds of this happening are like 1 trillion to 1, and that's not even close to accurate.
Simple chemistry. This is simple chemistry.
Yeah. This can happen. This can happen even outside of a living system.
Right. Okay, so you have an N here, and you have two C's, basically. And we have the R group up here, the side chain. Okay, so this is a
it is the side chain, which is itself hydrophobic or hydrophilic, right?
Yeah. That determines the properties. This core chain. There is attraction between these nitrogens and oxygens over here. Basically, they'll hook up and they'll fold. These two kind of want each other, sort of. And, well, the hydrogen and the oxygen, basically. So you can have hydrogen bonding, basically. But anyway, so this is the backbone of a protein. This one doesn't belong. It belongs to another protein that's over here, or another amino acid over here. So we have the N, we have the C, CB, beta, and C alpha, basically. So the let me see. Why do they draw that beta? I've always taken that one as beta. Anyway, okay. So this one has the R group, the side chain, and this one has the side chain on the other side. Okay, and this kind of shows how they fold. So we've got this zigzag because these things tend to, alkanes, like if you just hook up the carbons, they tend to arrange themselves so that they're not touching each other. They don't like to touch. Like, don't touch me, that sort of thing. So anyway, they kind of rotate around these bonds, and this carbon bonds can rotate 180 degrees, go all the way around, right? So carbon bonds are pretty easy to rotate. The carbon nitrogen bond is, let me see, that's psi. Okay, that's psi, and that's phi. Let me see here. Where's psi-phi? Okay, psi-phi. It's not showing. Okay, that's phi, and that's psi. Okay. Something's wrong here in my head. I think I'm getting tired. But anyway, sci-fi, like the sci-fi channel. Okay, that's phi and that's psi, basically.
Yeah.
These are the two different rotations of the bonds. And basically now we're ready to do another video where we talk about protein folding. Okay?
All right. I'm looking
Uh,
forward to
organic, organic is the best chemistry. That other shit is bullshit. It's just bullshit.
that.
But anyway,
No,
so this kind of
physical chemistry is pretty cool. I like
yeah, it
blowing
sucks.
stuff up.
Yeah, it bores me. Anyway, so this is basically the backbone of a protein, and this is how they
Mhm.
fold. And it's kind of a little bit of the
Yeah,
geometric
we're
puzzle.
talking about a combination of electron bonds, valence electron bonds. We're talking about hydrogen bonds, and we're talking about some ionic side chains influencing how they bond. And that all influences every stage of the protein structure, the primary structure, the secondary, tertiary, and quaternary structure.
Yep. It shows you another
So-
picture with the peptide bond,
Yeah.
which forms between these two amino acids, 1 and
Mhm.
2. And it shows you the same description, and it kicks out of water. So it's dehydrated. Okay.
Yeah.
Every time two amino acids stick together, you get a water molecule.
Mm.
It's kind of a nice picture for that. And it's another picture of the structures of the amino acids at 20. You'll find that if you search for amino acids on Google, click images, and you'll find all of these. I'll give you.
Yeah, so more and more as I'm studying chemistry, I'm thinking of just getting a series of chem tattoos, so I don't
Oh,
have
yeah.
to memorize all this shit. Just get
Oh, you want a
tattoo
tat?
right on.
You want?
Yeah.
You need 20 tattoos to get all
Let's
of
get
these on there.
Let's get some amino acid tattoos.
You want to get amino acid tattoos?
I think it would look cool.
Yeah, and I think we're starting over again. So yeah, okay, I'm done.
Yeah, if you want to wrap it up there, I think we've covered a lot of information. If there's any like main points you want to reinforce before we kind of close this one out and say, take what we've taught you so far here and let it gestate a little bit, and we'll cover more later. I think that's a good
Yeah.
idea. But yeah, are there any main points you think we should take away, Mike?
Well, if anybody can find a book by Isaac Asimov, do you know who Isaac Asimov is?
I love Isaac Asimov.
Okay, he wrote a lot of nonfiction books. One of them
Sure did.
was called The World of Carbon, which I picked up when I was very young, probably 12, 13, something like that. And The World of Nitrogen. They're no longer in print. I do have copies of each, but if somebody can find PDFs of those books, what he does the same thing I did. He starts with just that one carbon. He shows you the alcohol. He shows you the carboxylic acid. He shows you the amines. He tells you why fish stink. He goes through and he does this wonderful job of explaining carbon chemistry. But it is extremely readable and interesting, unlike my videos. So
I should easily be able to get access to that book because I literally work at the place where they digitize books. So I should be able to find it.
See if you can find that because they quit printing them for some reason. Every school kid should be handed.
Take a note down. You said the name of the book was The World of Carbon?
I'm putting the
and-
link to it right now in the side chat.
Good, thank you. And
Thank
The
you,
World
Scott.
of Nitrogen. World of Nitrogen's the other one.
They're two separate books?
Yeah, two separate. They're little books, and it's Isaac Asimov style readable. And he wrote, Foundation and a lot of really great science fiction. But Isaac Asimov is great. But anyway,
he's known for the 3 rules of robotics. That was
Yep. So to wrap up, so these are the amino acids that we showed in greater detail, all hooked up into a chain. And you can see that one amino acid is a little bigger than you might think. When they show you these pictures, you think, oh God, there's billions of amino acids. No, that's one amino acid that every square I light up. So you can have an alpha helix with as little as 3 amino acids, I think.
What program are you looking at this on, Mike?
I linked this in the video I did a couple days ago, and it's called AlphaFold. It is the
Oh,
AI
AlphaFold.
program.
That's right. Okay,
Yeah.
AlphaFold.
And if you go up here, and type in, where are we here? AlphaFold protein structure database. Okay, where's search? Why don't I have search? Oh,
And
Yeah.
like T was explaining to us when we had him on, this data set is so important to dig into and understand, because understanding how proteins are supposed to fold helps us make sure that they do fold properly, which is huge for preventing diseases. Like one of the biggest diseases it can help prevent is the big C itself. So there's a reason this shit is important, and scientists are trying to crack this mystery, and they're getting really freaking close. I feel like, Mike.
Oh yeah, they're especially with AlphaFold.
Yeah, 100%.
Yeah, you see, these things are called disordered. Basically, they're disordered amino acids. They kind of form all these loops.
Real quick before we pivot to that, this is why it's fucking important to teach kids evolution, because nobody's gonna be able to fucking crack this shit and cure cancer without it.
Nope.
Yeah. Sorry, I got a little heated there.
I know, you should. There's a nice big alpha helix here. Here's some small helices. Anyway, so you can look up any protein you want in this database. So anyway.
Yeah. Super cool. Thank
but
you
I want to
so
wrap
much
it up.
for the lesson, Mike. Yep. Absolutely. Okay. We can wrap it up there. Thank you to the audience for watching. Thank you to everybody who's rewatching the stream, who's studying and learning from it. Like, subscribe, leave some comments, ask us questions. I'm sure Mike would love to answer and ramble more about it. Yeah.
But I've forgotten most of everything I know, so just give me a break. Okay,
right,
so here we have World of Nitrogen, and here we have World of Carbon.
Actually,
and
the second
I have these
also World of Carbon. I forgot to copy the actual link to World of Nitrogen, so I'm going to repost it.
Okay.
What is ZLab? Did you find PDFs of these things?
Yeah, on archive.org.
Nice.
You're kidding.
Yeah, I don't know that it's downloadable, but it's readable from there.
Yeah.
Holy shit. Oh my God. Yeah. If you read these books, Austin, you will view, like, my great niece hated organic chemistry. A lot of students do because of the way they teach it. If you read these books, you will love organic chemistry.
Yeah.
You'll learn to.
They teach it kind of like the way I was talking about earlier, where it's just you're memorizing huge amounts of facts by just like rote and pouring over them so much that they get stuck into your brain. You're talking about a model where you're being taught via an engaging narrative, which I think, is usually a better way to learn.
Yeah. You guys out there listening, I really appreciate you listening. It gives me heart when I see at least 5 of you out there, and we've had like 9 and 10 here, so thank you.
There's 9 watching on your channel, and there's like 6 or 7 watching on my channel, so we have like
no shit
15 or 16. Yeah.
Well, awesome. Okay.
Yeah.
Anyway, and I'd love to answer questions about this, but the thing that going back to the 30,000 foot view, or whatever the hell it is, 10,000 foot view. You want to look at how carbon can fold up and form all these complicated chemicals like Vaseline and gasoline and all of that shit, and acetic acid. And the next thing to look at is how, when you get into the amino acids and they start hooking these protein chains, how many different ways they can fold up, right? And do unique things. And the creationists just, they talk about believing in God's glorious natural world. Well, they're blasphemous. They shit on it all the time. They look at it as a machine that has to be designed by some dude. Okay. No, this complexity is God. I mean, this is like your God, the complexity of the world of carbon and the world of nitrogen. So tell them to go fuck themselves and blasphemers.
I have talked to a lot of people who say that creationism is heretical, and I gotta agree.
Yeah, it is. Yeah. I mean, it just, it misses the whole fucking point of the complexity and the wonders of the universe.
Absolutely.
It reduces astronomy to this one planet with this one species that's supposed to be so special, and you got a whole universe out there, for Christ's sake, and it reduces basically chemistry and all this complexity to, there was a dude sitting around and he was an engineer, like God was a good engineer and he had a pencil and he drew all this bullshit.
Engineer.
Any engineer that would design this should be fired.
Oh yeah. He's a fucking artist. I mean, this is art. This is not engineering. This is art. What were you gonna say, Scott?
I said those engineers.
Oh yeah.
They want all the credit and glory.
They suck. I love this little guy. Anyway, okay, guys, we're gonna end it.
Cool. Yep.
Wrap her up. Okay, we're gonna end the stream. Subscribe to my channel. I'm gonna die soon, so I'm really old.
Yep.
And goodbye, cruel world. Gonna end the stream.